Yeah, first of all, thanks for inviting me to speak here. It's nice to be back at this place. So I'll give 3 lectures. They're devoted to a paper with Johannes Nicaise. And this paper explains the sort of method you can use to attack rationality problems for hypersurfaces and complete intersections. So these are quite classical topics in algebraic geometry, and this paper sort of takes inspiration from motivic integration techniques and applies them to solve some new cases of the rationality problem. So this lecture today will be devoted to sort of the classic background, and then I'll explain the main results tomorrow on Friday. Okay, so the basics. Let's say that 2 varieties, x and y, are stably birational if they become birational after taking products with some projective spaces. So 2 varieties are birational if you know, there are open isomorphic subsets on both, and we say that 2 varieties are stably birational if they become birational after taking a product with projective space. And x is stably rational if it's stably birational to a projective space or stably birational to a point. So of course we care about stably rational because we care about rational. So this is a sort of, it's a notion that's sort of close to being rational. And if we can prove that something is not stably rational, we have proved that it's not irrational. Not rational. It just turns out that this notion is sort of a little bit more flexible than rationality, and then sort of all the techniques typically work for this. So in this talk, this will be sort of the most important notion. Okay, so and the rationality problem is just to, you know, if I hand you a variety, ask, you know, you should determine whether the variety is stably rational or not. And this is, of course, a very difficult and classical problem in algebraic geometry. And one very important case is the case of hypersurfaces. And that is basically asking, you know, for which degrees and dimensions is the degree d hypersurface of dimension n stably irrational. And typically we ask about general, so it's not like we're handing a concrete polynomial. We ask, you know, when is the sort of the random hypersurface in Pn irrational. Okay, so I have 3 lectures. This is not so much, and this is sort of my goal to understand this result here. Well, there are actually 3 results, so but this is what we'll try to cover. So the first is one instance of this rationality problem for hypersurfaces. It's just saying that a very general degree 4 hypersurface in projective space is not stably rational if the dimension is at most 5. Yeah. So that means that, you know, in P6, if you take a quartic polynomial, random one, then this will not be rational. So there were some results on this before. These cases, like for low n, of course, this is known, but I'll try to survey a little bit about which degrees were known before. And the next result is about degree 5. Here we can sort of go all the way to 13. Very general degree 5 hypersurface is not stably rational up to dimension 12. And the next one is a complete intersection. So this is one new case of Fano varieties where we know that the very general intersection is So you take a quadric and a cubic, and now we know that this very general intersection is not stably rational. So just one word about this very general. It just means that you have a parameter space, and the property is supposed to hold outside a countable union of closed subsets. So it's not, it still holds for sort of most hypersurfaces, but it's not like you can choose them in an open set, because you might need to remove infinitely many things. So that's what very general means. Okay, so in my opinion, the most interesting result is this. So I'll try to at least explain this. But the whole paper it's a technique that applies also to these cases. So that will be the sort of the goal, to understand that technique. Okay. So just a little bit of overview of the proof. It uses the recent results on specialization of birational types. This is due to Nicaise and Shinder, and then later extended by Kontsevich and Schinkel. Also we need some efficient way to degenerate things, and we use toric degenerations in tropical geometry. And then there's some input of irrationality from lower dimensional varieties. So all three, all of these three ingredients are needed, and I'll try to highlight where they come up. Maybe before we start, let me just say a little bit more about this rationality problem. The rationality problem is usually about how to prove that a certain variety is irrational. So you want to find obstructions to being rational or birational invariants, and there are a few very basic ones, like topological invariants. Like if rational varieties are simply connected, so an elliptic curve is not rational over the complex numbers. Another basic invariant is just the space of global p-forms. This is also way too naive to be interesting in this context. The Brouwer group is much more interesting. So this is something that will show up in these lectures. And then towards the end of this lecture, we'll encounter this decomposition of the diagonal technique, which is a more recent technique, which allows us to prove the varieties are irrational. Of course, so you look for an obstruction, and then you try to show that the obstruction is non-trivial. And this is this is a sort of delicate thing. So typically, in these lectures, we'll try to verify that it's non-trivial by sort of specializing to a singular variety. So singular varieties are usually considered quite bad, but in our world, it's nicer because they typically have more invariants. You can sort of, because they're so singular, you can sort of compute things more easily. So I'll try to explain this. Okay. Let me say a little bit more about hypersurfaces. So there's a sort of chart we can plot. So here we have we have the dimensions up here, and then the degrees. The degrees down. Everything is that you see in green is rational. The degree 2 hypersurfaces, they're all rational. And then you have this sort of outlier here, which is the cubic surface. Everyone, we've probably seen that this is rational. And then we have everything in red here. These are sort of easily proved to be irrational just because they admit global holomorphic forms, and you can't have that as on a rational variety. Yep.
You mean that it's never studied rational in these cases, or maybe?
Oh, I mean, well, what you see here, they're never. Like anything that's smooth will not be rational. But exactly your point will show up in the other places in the diagram. Okay, and in the 70s, there were two sort of breakthroughs for threefolds. So one was about cubic threefolds. One, well, by Clements and Griffiths, who proved that any smooth cubic threefold is irrational. And the obstruction that they used was the intermediate Jacobian technique. So this is some abelian variety that you can study, and if it's rational, it has it sort of decomposes into a product of curves, or Jacobians of curves. I won't say so much about this. There's also the classic work of Iskovsky and Manin, who considered the quartic threefolds. So here the birational morphism group is the invariant, and they prove that if you have a quartic threefold, this automorphism group is finite. Whereas, you know, if this was rational, it would be, you know, the birational automorphism group of P3, which is enormous. So this is one way to see that this is irrational. Okay, then it turned out that the method of Iskovsky and Manin, it really gave all of these other cases down the diagonal here. And then Kolar, so this was in the 90s, he developed another technique that gave sort of infinitely many new cases, including like the, well, degree sixfolds. Yeah. Okay. Actually, in the interest of time, I think I'll just skip Kolar's proof. Actually, I should have mentioned this earlier, but I'll put the slides up online, and I'm also writing some lecture notes. So if you really want to see like proofs of statements here, you'll be able to if you want. So I'll just skip this for now, but it's a sort of a clever argument that yeah, it works in some cases, but it will not show up later in the lectures. So. Okay, what I wanted to mention was this example of Arthur Memford, which was also around 1970. So they used a stable birational invariant, namely the torsion part of H3. So now we're over the complex numbers. And if you look at the torsion group in H3, this is a stable birational invariant. Well, it's clearly 0 for projective space. And one can check that, well, if you blow up a point or a curve on this, or yeah, on a threefold, oh, not a threefold, but anything, this is how the H3 changes. And the amazing thing is that the new term that you get, this H1 of the center, it has no torsion by the universal coefficient theorem. So, you know, the torsion part in the blow-up and the torsion part in the original variety, that's the same. So you don't get more torsion by blowing up. And you see that it's really like H3, which is sort of the only thing that you could consider here because of this. I mean, you could consider H1 or H2, but you know, that would be sort of too easy.
What does E mean here?
It's the exceptional divisor. So here,
yeah, okay.
Yep, it's just a description of the blow-up. Sorry, the cohomology of the blow-up. Okay, so this is sort of very basic birational invariant, but it's interesting because many varieties that are sort of close to being rational, they have a non-trivial Artin-Mumford invariant. Unfortunately, this is non-trivial for rather special varieties. So what the Artin and Mumford proved was that there are sort of double covers or singular double covers, and their resolutions have torsion in H3. So there's some, equations, some like quartic polynomial in 4 variables, and when you take P3, the double cover of P3 along on that quartic, you get something singular, and when you blow up the singular locus, that has H3. So this invariant wouldn't appear on any hypersurface because those do not have torsion in H3. So, but this is still interesting because these threefolds are sort of close to being rational. They're unirational, meaning that there's a dominant rational map from P3 into X. So there's a sort of degree. It's not a one-to-one map, but it's a degree 2 map. So this X is very close to being rational, but it's not rational because it has a non-trivial Artin-Mumford invariant. Oh yeah, and yeah. Here again, this the word Brouwer group shows up. In this example, this is in fact the whole Brouwer group of X. So the way that you can actually construct classes in H3 is just by sort of interpreting this group as the Brouwer group and work with maybe Brouwer-Severi varieties. Okay, then let's go back to the chart. Just maybe 10 years ago, then there was sort of a new surge of results on this irrationality problem, sort of coming from the decomposition of the diagonal technique of Claire-Voisin, and later improved by Kollutolén and Pirutka that you see here. And they improved this Iskovsky-Manin result, who had earlier showed that these quartic threefolds were irrational, and now they prove that they're stably irrational. But now we have to sort of be precise. We know that the very general quartic is stably irrational. So these, here in red, every smooth is irrational. And in pink here, we know that the very general one is stably irrational. So there might be some like isolated or some smaller locus of irrational but stably rational quartic, but this is unclear. Okay, and this decomposition of the diagonal technique was extended by Totaro, who proved that degree 4 fourfolds are irrational, and then the best result is due to Stefan Schreider, who proved these cases over here. But his bounds are sort of very good in higher dimensions. So there's a sort of logarithmic bound that you, so asymptotically this is very, very good. And these lectures are filling in this yellow box. I mean, there are a few more yellow boxes out there, but at least I'll try to explain why this one is stably irrational. So that's the case of the quartic fivefold, and it's sort of So the quartic fivefold is really the only new case. So even though we sort of give new proofs of these earlier results as well. Okay. Let me say a little bit more about the decomposition of the diagonal. So what is this? Well, you take the diagonal inside the self-product, x cross x. And we say that x admits the decomposition of the diagonal if you can decompose the cycle, the diagonal, as, well, some sort of fiber, and then some cycle which does not dominate x with the first projection. So it's a little bit like you take the diagonal and you decompose it into like a vertical and a horizontal piece. So, you know, for projective space, this is clear. Like if you take P1 cross P1, the diagonal is just a 1-1 divisor. So you can sort of just write it as a sum of two fibers. And all projective spaces have this property here. But most varieties do not. I mean, it's sort of rare that you can decompose the diagonal inside the Chow group in this way. And this is, in fact, a birational invariant. So, yeah, for Pn, you do have such a decomposition of the diagonal. Probably seen this. This is a nice exercise for maybe the afternoon session to prove that having a decomposition of the diagonal is a birational invariant. This is a sort of nice exercise using blow-ups and Chow groups. Okay. Is that okay? What it means to have a decomposition of the diagonal? It just means that in the Chow group you can decompose the diagonal cycle as vertical and then horizontal. Okay. The point is that if you look at the diagonal as a sort of correspondence, it acts as the identity map, whereas a cycle of this form acts in sort of a trivial way. So let me just give an example that illustrates this. So let's show that a curve of positive genus does not have a decomposition of the diagonal. So the point is that if you look at x cross x, you can let the diagonal act on the space of one forms. So if you take a cycle like this, I mean, you can pull it back to the self-product, intersect with the cycle, and then push forward. This is how the action of cycles is defined. So here, if we take the cycle big X cross little x, well, it's a fiber, so you pull omega back via the first projection, you intersect with this, and then you project. But because this, well, x cross x, you know, maps to just little x on the second projection, this is just 0. And the same thing happens with the z here, because we assume that z does not dominate the first projection, and that means that z maps to a point. So z is also a fiber, or a union of fibers. So that means that when you do this computation here, you also just map to 0. But that means that you cannot have an equality, like the diagonal cannot be this, because the diagonal acts as the identity map. Yeah, so this is sort of one easy way to see that if you have a decomposition of the diagonal, you cannot have any non-zero p-forms like this. So having a decomposition of the diagonal means that you have, I mean, a lot of the cohomology groups have to be 0. Otherwise, you can apply this argument. So more generally, if you have a decomposition of the diagonal, well, the same argument shows that you cannot have any non-zero p-forms, global. And also you can let the diagonal act on the torsion part of H3. And you see that also there, you cannot have any torsion. So this is one invariance that sort of generalizes the previous birational invariance. Okay. Good. Let me be a little bit more precise what I mean about specialization here. So if we start with a family of varieties, which I mean family of varieties means a flat map. We can ask, how does the fibers, I mean, how does like the rationality of the fibers move in the family? So if I have some like curve in the base and I have some family of varieties, you can ask, you know, is the general fiber rational or not? We can also ask about the Chow groups of the fibers and the cohomology groups. Actually, the cohomology groups are kind of, I mean, this is easy because, well, at least in the smooth case, all of the fibers are diffeomorphic. So, you know, they, at least over the complex numbers, they're diffeomorphic, and then all of them, all of the cohomology groups are isomorphic. But the Chow groups can, I mean, this is one difference between algebraic geometry and topology, that the Chow groups can really move. I mean, they can really change in the family. And also the stable rationality also moves in the family. So, yeah. Let me try to give some examples what can happen. Like if you have a family of varieties, what happens to rationality? So the first example is that you can have a family of rational varieties that specialize to something which is irrational. And of course, it's a familiar example. You take a family of cubic surfaces, maybe like the Fermat, like this. So if you have B non-zero, then this is just a smooth cubic surface. So we know that this is rational. But if you specialize, if you put B equal to 0, this is the cone over an elliptic curve. So it really looks like this cone here. And this is not rational because if you blow up the singular point here, you really have like something which is, you know, elliptic curve times P1. And, you know, it's not even simply connected, so this is not rational. Okay, but that says that if you have a smooth family of varieties, it can specialize to irrational if you allow like this kind of horrible singularity in the special fiber. You can also have irrational varieties that specialize to rational. Maybe this is even more basic because you can have elliptic curves in the plane that specialize to a nodal cubic. Oh, sorry. So elliptic curves are irrational, but nodal cubics, because of their singular point, they are rational because when you take the singular point, you can project from the node. So it's sort of famously rational, this curve here. But again, you have to sort of go from smooth to singular before you sort of see a change here. Okay, and the classical question here is, you know, what can happen if you have a family of smooth varieties? So where all of the fibers are smooth. So if we take, for instance, a family of surfaces, then if x0 is rational for some fiber, then all of the fibers are rational. This is kind of a, you know, it's a remarkable statement because, you know, you just know that on one fiber there's some birational map from P2. And there's no way or no reason why this should sort of deform to the other fibers. But it's because of, you know, for surfaces, you have a sort of a cohomological criterion to be rational. It's this classical result due to Castelnuovo saying that if these groups here are 0, then your variety is rational. And if you have a smooth family of complex varieties, these cohomology groups, they vary continuously, or the ranks. Okay, so if you know that there's 0 on one fiber, they have to be 0 everywhere. Okay, but here is a sort of more wild example, in my opinion. So if you take a 2-2 divisor, so in P2 cross P3, that means that we have two sets of variables, x's and y's, and we take some equation which is of by degree 2 and 2. Then, well, Hassett, Pirushka, and Schinkel, they prove that if you choose this equation to be very general, then x is stably irrational. So most 2-2 divisors are irrational. But there are some smooth rational ones. So if you choose the equation to be of this form, so here I think of the variable, you have some x's here and y's here, then this is actually a rational variety. The point is that if you have x0, x1, x2, and x3, and you have an equation of this form, it has to be linear in x3. So it means that, well, if you have a linear equation, you can solve it, and so this equation is actually irrational. But that's kind of strange because that means that most are irrational, but you can sort of just go to some special equation and then it's actually rational. So you can have irrational specializing to rational. Okay, this is just a summary. Okay, so most 2-2 divisors are stably irrational. There are also countably many divisors in the parameter space that correspond to rational ones. So you have some big projective space that parameterizes 2-2 divisors, and then you have infinitely many divisors where you do have rational fourfolds like this. And this is another exercise for the afternoon session. If you have any family of varieties, we can form the rational locus. That's just the set of points in the base where the fiber is rational. And the exercise is to prove that this is a countable union of locally closed subsets. Yeah, and the keyword here is to use a Hilbert scheme argument. Okay. Let me try to say a little bit more what I mean about specialization. So I'll work in a general setting, so R will be some discrete valuation ring, and X will be some integral R scheme. And this is sort of a typical diagram. So we'll have some family over here, and then we'll have the base change to the generic point, and the base change to the special, or the closed point of the DVR. So we call K the fraction field of R. This is the fraction field. Little k is the residue field. And we call, this is the generic fiber, and this is the special fiber. It's just the typical, or the standard terminology for specialization. So the picture to have in mind is the following. So you have some, this is what spec R looks like. You have some sort of big generic point, and then you have a special point, the closed point here. And a typical situation is that we have some smooth generic fiber, and then it specializes to maybe a union of varieties like this. And we say that a variety X specializes to a variety Y if X is, if there's some curly X where you can put X here and Y here. So yeah, this is what I mean by specializing to a variety. It just means that the variety is the generic fiber, and then the specialization is this special fiber of some flat map. Okay. In this setting, there's this very useful map on trial groups. Like if you take some subvariety of the generic fiber, well, because this is dense, you can sort of just take the Zariski closure and any cycle here will give you a cycle here. So that means that you get a map on Chow groups from the generic fiber to the special fiber. It's really take the closure of the cycle. So it's a very, it's something that really exists in the world of algebraic geometry because we have this Zariski topology. So here we are allowed to take closures of things. Okay, so we have a specialization map of on Chow groups. So it goes from the Chow group of the generic fiber to the special fiber. Okay, so let's go back to this property of having a decomposition of the diagonal. So the point is that having a decomposition of the diagonal, that's something that only involves cycles. So it's asking whether some equality happens in the Chow group. And because it's a cycle theoretic condition, it's very well suited to apply specialization arguments. Like in general, if you look at topological invariance, if you take a generic fiber and then you try to specialize, that's not going to work because you can't specialize this. You can't specialize by rational automorphisms or stuff like that. But the decomposition of the diagonal, because it only involves Chow groups, that means that it's perfect for degenerating things. So here's the sort of strategy. You specialize, the variety that you want, maybe a hypersurface or something. You specialize to a singular variety, x0, so that this x0 does not have a decomposition of the diagonal, or maybe this special fiber. Sorry, this is supposed to be the same. It's not supposed to be script here. Okay. So if you can specialize your hypersurface or something like that to some variety where maybe some resolution has non-trivial homology groups, then you don't have a decomposition of the diagonal. Or you have to sort of specialize so that, the homology groups I had in mind was these, the homology groups from before, the P forms or the torsion in X3. Okay, but then if there's no decomposition of the diagonal on the special fiber, then X does not have a decomposition of the diagonal either. Right? Because if you have a generic fiber and some equality happens in the Chow group, you can just specialize that to the special fiber, and then you have a decomposition of the diagonal. So if you're lucky that you can sort of degenerate to some variety where maybe on some resolution there's some homology groups that sort of prevent having a decomposition of the diagonal, you can actually deduce that the generic fiber does not have a decomposition of the diagonal either. And hence X is not rational. So this is the sort of a very basic specialization argument. And I think this is sort of the takeaway from this lecture here today. So this could even work for a hypersurface. You can degenerate a hypersurface to something singular, and then try to obstruct the decomposition of the diagonal, provided that this x0 has this property. Oh, and also one has to be careful. This is a very subtle argument. If you try to apply it to the elliptic curve example, then you have a family of rational varieties. So these cubic surfaces that we had, they specialize to a cone over an elliptic curve. So of course, cubic surfaces do have a decomposition of the diagonal, but a cone over an elliptic curve does not have that. So this argument is not automatic. It's just one has to sort of control the singularities for this to work. So I'll explain what this means next time. But let me just show you one example where this argument is used. Okay, so the argument will involve quartic threefolds. So we have quartic polynomials in P4. And it's possible to write down a degeneration so that this is birational to the Artin-Mumford example. Well, you can write down explicit formulas, but I'll also, well, next time I'll show you exactly how to do this. But the point is that you can do this. So the quartic threefolds can be specialized to something which is birational to the Artin-Mumford example. But the Artin-Mumford example has this property that some resolution has non-zero torsion in H3. Oh, yeah, sorry. This has mild singularities. And yeah, this Artin-Mumford example has a resolution where you have non-zero H3. So that means that the special fiber does not have a decomposition of the diagonal. But that means that the nearby fibers also do not have a decomposition of the diagonal either. And so the very general XB is not stably rational. Oh, sorry. Sorry about this. Yeah. I really think this is a nice idea. So this goes back to Claire-Voisin and Colotole and Pirotka. So quartic threefolds do not have torsion in H3, but they degenerate into very singular things that do have torsion in H3, and that's sort of the point. Whereas the diagonal, that you can sort of specialize. So it's a really nice argument, I think, that really sort of relies on the fact that you can specialize cycles, but this torsion thing, it's much more complicated to specialize. Okay. I think this is maybe what I wanted to say for this talk here. As I said, I'll put out the notes for the talk, and yeah, we can discuss the exercises later.
We have time for questions.
So comments?
Yep.
At the slide where you showed that if you have a global differential form, you well, your argument was that you pull back this differential form by the diagonal, and it is still the same differential form.
Yep.
But well, it lives in the.
Yeah.
Like, could you give more details of that argument, please?
Yeah. So it has to do with how you define the action on cycles as a correspondence. So what I maybe should have done was to say that. Well, okay. Yeah, maybe I'll write over here. Like if you have x cross x, and then some cycle in the self-product, you can let gamma act as follows. So you take some class. So maybe let's work with just complex cohomology. Then what is this? Well, you're supposed to pull the class back. So you take the first projection, and then you intersect. Maybe take the cup product with gamma, and then you can use the. I mean, you can take the Poincare dual, and then you push forward. So this, I mean, here, I mean, when you pull back, that's cohomology. And when you push forward, that's homology. So, I mean, this is how you, I mean, everything here is smooth. You use Poincare duality and then you push forward.
So it's only true for smooth variety?
No, I mean, you can do it more generally. You just need some way to define the actional correspondences on cycles. Yeah, so it's just coming from the basic action of correspondences on cohomology. But maybe this is something we can discuss in the afternoon. Yeah.
Other questions?
Your results were for very general varieties. What if the base field is countable?
Yeah, a good question. I'm not sure if you can actually make it. I mean, it's possible to write down explicit equations that involve some transcendental parameter, like pi or something like this. But over Q, for instance, I think this is quite difficult. So, yeah, this argument that I'll actually, well, that I explain here, then that I think only works for uncountable fields. But there are ways to get around it, especially with this decomposition of the diagonal technique. Because you can, instead of specializing, you can take the reduction mod some prime number. So then you can start with polynomials with integral coefficient. You can reduce maybe modulo 5 or something like this, so that, you know, modulo 5, it becomes the Archimedean example. So this is one way to make explicit examples with integral coefficients even. But my result, I'm not sure if we have equations over Q, for instance.
Questions again? Okay, so we thank the speaker again. And